Type 2. Exact number of successes, binomial distribution. Suppose a single Bernoulli trial has a probability of success P and a probability of failure Q. If this trial is repeated 6 times, what is the probability of getting exactly 2 successes? If there are 2 successes, S, then there must be 4 failures, F, in the 6 trials. One way this could occur is success and success and fail and fail and fail and fail. The probability of this occurring is P times Q times Q times Q times Q times Q, which is P squared Q to the power of 4. But this is not the only way we could get 2 successes and 4 failures. And each way has the same probability. So we need to find the multiplier. This is the number of ways of choosing 2 out of 6 positions to put the success in, and failures automatically occupying the other positions. From combinations, the multiplier is 6 choose 2. If we let the random variable x stand for the number of successes, which we're interested in this case is 2, then we can write what we want as the probability of x equals 2. Thus, the probability of x equals 2 is 6 choose 2 times p squared times q to the power of 6 minus 2. So basically the 6 is the power of the q, and the 2 is the power of the p, and we also subtract the 2 from the 6 from the power of the q. And 6 take away 2 is 4. So you end up with 6 choose 2, p squared q to the power of 4. So this part we already had from up here, and the 6 choose 2 we got from combinations, choosing 2 out of 6 positions. This is the multiplier. In general, if the random variable x stands for the number of successes in n Bernoulli trials, for which the probabilities of success and failure in a single trial are p and q equal to 1 minus p, so remember p is for success and q is for failure, respectively, then the possible values of x are going to be 0, 1, 2, dot 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 up as far as n, i.e. x will be an element of 0, 1, 2, dot 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 up as far as n. The probability that x is equal to or, i.e. that we have or successes in the n trials, is given by the probability of x equal to or, which is equal to n choose or times p to the power of or times q to the power of n minus or. So we actually worked with this formula in the last slide, we just didn't use the actual formula. So whatever your x value is, that becomes the number on the bottom of your choose function, and it also becomes the power of p, and the n becomes the power of q, and you're going to subtract the or, which is the x value, from the n for the power of q. So that's how this formula works, and this is on page 33. The distribution of x, along with the associated probabilities, the probability of x is equal to or, for or greater or equal to 0, less than or equal to n, is called a binomial distribution, as each probability is a term in the binomial expansion of q plus p to the power of n. Binomial distribution, or successes in n trials. Suppose a single Bernoulli trial has the probability of success p and the probability of failure q. Then the probability of exactly or successes in n trials is given by the probability of x is equal to or, which is equal to n choose or, times p to the power of or, times q to the power of n minus or. It is important to realise that the formula for the probability of x equals or says nothing about the order of the successes and the failures. So let's have a look at an example. A die is thrown 8 times. What is the probability that we get at most 2 6s? So the Bernoulli trial is throwing a die. For this, success is getting a 6 And P, which represents success, is going to be equal to 1 over 6, because there's 1 6 on a 6-sided die. Failure is not getting a 6. So failure is represented by Q, which is 1 minus a 6, which is 5 over 6. Let X be the number of 6s we get in 8 trials. If we have to get at most 2 6s, then X is equal to 0, or X is equal to 1, or X is equal to 2. We will calculate the probability of each of these and then add, as these events are mutually exclusive. For single trial, success is getting a 6 and failure is not getting a 6. Thus, P is equal to 6 and Q is equal to 1 minus a 6, which is 5 over 6. For the experiment, N is equal to 8. The die was thrown 8 times. Let X be the number of successes. We want the probability that X is less than or equal to 2. So the probability that X is less than or equal to 2 is the probability that X is equal to 0, or the probability that X is equal to 1, or the probability that X is equal to 2. Remember, or means add. So we're going to follow this formula, and we're going to swap the or for 0, then 1, then 2. We're going to swap the N for 8 each time, because it was 8 times that the die was thrown. We're going to swap the P for 1 over 6. We're going to swap the Q for 5 over 6. So the probability that X is equal to 0 is going to be 8 choose 0 times a 6th to the power of 0 times 5 over 6 to the power of 8. Because 8 minus 0 is 8. And this gives us 0.23257. The probability that X is equal to 1 is going to be 8 choose 1 times a 6 to the power 1 times 5 over 6 to the power 7, because 8 minus 1 is 7, and that gives us 0.37211. The probability that X is equal to 2 is going to be 8 choose 2 times a 6th to the power 2 times 5 over 6 to the power 6, because 8 minus 2 is 6, and that gives us 0.26048. And adding them, we get 0.86516. So this is the probability that when a die is thrown 8 times, we get at most 2 6s.